Hello again, and welcome back to Information Storage and Retrieval. We are going to get into today what is the sort of lifeblood of modern search, modern unstructured information retrieval, the inverted index. It's this is a more intuitive thing than you might be expecting up front. We'll get into why, but we'll also be walking through how to build one in concept. Now, we are going to touch on a few areas that we will continue to dive deeper into in later lectures. Just try to keep repeating the steps in the order that we need to do them to create these very useful tools. So, first, recap. What were we on about last time? The term document incidence matrix, right? This is still a useful retrieval structure. If I'd rather do this, I'd rather have this big giant board of where everything lives in my document collection than having to search through it by brute force. But there's a lot of limitations here. Because remember, we are always working with limited processing power. Even if you're Google, even if you have all the processing on the world, you still can't be wasting cycles trying to build something, trying to build these structures, but also trying to use them to look things up, right? So the issues with the term document incidence matrix are that it just grows way too large too quickly. It scales poorly in terms of size. There's always going to be a number of cells in your matrix equal to the number of documents in your collection times the number of terms, and as those approach huge numbers for documents and the entire English language and more phrases for your terms, that's just an unwieldy structure. On top of that, even though it's very large, it's also not full of useful information. For every term, there's going to be millions of documents that term does not occur in, but we're still going to record a zero for it. We're going to be saving a place for a lack of information. So, getting away from the term document incidence matrix, what's a better structure? Well, this is where we get into inverted indexes. So, this is second in our series on Boolean retrieval. Inverted indexes are the key. So, what is one of these things? What is an inverted index? An inverted index is a way of tracking only the places where the information does actually live in your collection. So, it consists of, very much like the term document incidence matrix, a list of terms, right? All these relevant words and concepts that we might want to search for. And then postings for each term, which is not a full array of length documents, but it is a list of the locations where those documents live that do contain that term and not the ones that don't contain that term. Where might you have seen this before? Well, if you've ever cracked a textbook open, the index. That is an inverted index. In fact, from now on, I will probably just refer to indexes as indexes, but the technical term is inverted index. We'll talk about why in a minute. But this is an index. This is the efficient structure, right? You have a term that you're interested in looking up in your textbook, and you have a page number that is the document ID in terms of pages being the documents in the book, right? So now, when you're like, oh shoot, where was that segment on Boolean operations, right? You go to the index, you sort to B, and very quickly you figure out, oh, it's on pages 149 and 178. That is how all this search works, but we are doing it in much more, large-scale computational terms and not just this nice lookup structure for a textbook. But they are fundamentally the same. So, why are we going this direction? What's good about these? First, they are sparse structures, right? They only keep track of where a particular term actually does appear in your collection. It's not holding on to a bunch of negative information of where it doesn't appear, because that ultimately doesn't matter so much, right? I'm only really concerned with where something does show up. And second, while these sorts of indexes can grow quite large, if you have, say, a lot of terms are common among a lot of your documents, say every document in your collection has a large overlap of the kinds of things they talk about, there will be a lot of page numbers associated with your document, right, or with your term. But typically, it doesn't grow like that. You're going to have a lot of terms across all your documents, and each term is going to show up in a few places, not every single document, right? So that leads to a very lightweight structure that allows you to fairly quickly say, okay, if I'm looking for these two terms, here's a short list of where they both appear. I need both of them. I'm going to narrow those two lists down and figure it out, right? So these are the backbone of modern search. And the basic idea of building these is we're going to do all the processing up front. I've talked at length about why we don't want to do all this brute force searching and linear scanning and all that. We still have to do it at some point to be able to build these structures, but we do that up front. We create this very efficient structure, and then that's what we will use to look up where information is stored. It sounds very straightforward, and in a sense, it is. But we're going to talk about all of the steps involved in creating the index, in collecting documents, and processing your query, all this good stuff. So let's talk about the process of creating one of these indexes from your documents, from your collection. So the overall process, today we will focus on constructing the index, but we'll talk about the other steps too. If I'm going to index some collection of documents, I'm going to first need to gather those documents somehow, right? We don't just get that for free. We got to find what are we actually building this search structure for, right? If I'm Google, it's every web page in the world, hopefully. If I'm Spotify, it's just all of the songs that I have in my database, right? Not every song that exists, because I don't care about every song. I care about the ones that I'm actually licensing, right? From there, we tokenize the text, kind of split this unstructured data up into little chunks, right? And then we process those tokens into terms. I'll talk about what that means in a moment. And then we build our index. Now, we talked about some of this for the term document incidence matrix stuff. We'll get a little more specific here. So, first, collect your documents. How do we do this? This is, it spans the whole spectrum, right? I can just do this manually. Just grab all of the documents that I care to index together. Maybe I'm trying to collect a specific set of information on my computer. Maybe I'm just trying to gather things from specific websites, whatever it might be, right? Another way is to crawl the web. This is what Google does, and this is what a lot of systems do. They set up little programs that will go out and find, hey, here is a page. I'll keep track of its address so that later we can pull out its text and chunk it up and build an index about it. Or we can gather, existing collections, right? This is more the Spotify thing of, this exists, like that people have uploaded their tracks to us. We've curated all that. I will build my index over this existing collection, right? So the reason I talk about this is that we have to build these indexes with a particular scope, and collecting your documents defines the scope of what you're going to be able to search. Okay, so now for each of these documents, we got to turn it into something that can be indexed, right? So we'll talk about tokenizing the text. Again, we'll cover these in depth later about different ways and reasons you might tokenize differently, but for now, the basic idea of tokenizing text is you will take a large string and turn it into many chunks, little substrings that can be separated out and used elsewhere. Remember, strings are text, right? The sort of a primitive in most languages is I can hold a lot of characters in one spot, a string, right? So to split a string, or to tokenize it, typically it's as simple as splitting it up based on, say, white space, right? Hey, look at that becomes hey and look and at and that. That's very simple, but it's critical because you need to be able to break these larger unstructured sets of data, the document text, into something that is more easily processable, right? I'm not going to run I typically will run a search on a couple of separate concepts that I want to see if they co-occur, right? So document text will get chopped up into tokens. Okay, great. So now we have tokens. Now we need to turn them into what is called terms. So we will take those tokens from the text and we will turn them into a common form. So text has a lot of different elements to it, right? There is punctuation associated with text. There's different capitalizations, all this stuff. A lot of times, these are all different ways of expressing the same core word or concept, right? So a term is the normalized and, in some ways, the idealized version of a word. Now, again, we can also have terms that are phrases and things like that. Again, we'll cover those later. But so cat, and cat, right? These are all different ways of spelling out the same concept. It's the idea of cat. I don't want my documents to be... I don't want my searches necessarily to be broken up around, like, to fail because I didn't get the capitalization right or because there was a piece of punctuation attached to the word that I wasn't able to find. So remember, when we are creating this index, we need to think about how the user will be experiencing it, right? If I type cat into a search, it should probably figure out that the word cat with an exclamation point after it is what I'm looking for, right? So we collapsed all these different terms into one common form of the term, and that is normalization. We are keeping track of where the concepts live, not just the raw text. Okay, so indexing documents proper. All right, so now we've got our documents chopped up into terms, just kind of sitting there. They're still in the right order. We're going to invert that. So the reason these are called inverted indexes is normal text are terms listed out in the document order, right? The order in which the words will appear in your document. Words in proper order, all in a row, right? An inverted index, the reason, and this is just to clarify why it's inverted, is we are now going to list out all the documents in term order, right? A term will have a set of documents that are associated with it. Basically, we're stripping out the natural language structure from the document and turning it into a sort of lookup system instead. So, what is in an inverted index? There are two elements to every index. There is the dictionary, which is the list of all the terms that occur, and there are the postings, the list of the documents for each of those terms. These are key. These are going to keep coming back because we're going to talk about all sorts of things associated with the dictionary and all sorts of things associated with the postings and how to process them and all this stuff. Just keep these two ideas active in your mind. And remember, I'm not talking about the dictionary where we have a word and we look up its definition. That is one kind of dictionary. And if you're familiar with programming, you'll know that there are other kinds of dictionaries. It's just a list of terms with content associated. The content in this case, in the inverted index, is the postings, the documents, where the documents are. Okay, so how do we build this? We can see it looks kind of straightforward, right? Oh, okay, well then I'll go through each word in the document and I'll pile it into the list. Okay, good. But remember, we're talking about the algorithms. How does a computer do this, and how does it do it efficiently? So, we will consult here a set of processes and a little bit of algorithmic stuff that will consistently build an efficient, well-sorted, inverted index. Let's do it. So how do we make a computer do this? First, we will record. Remember, we are running through these documents linearly, right? So how do we make sure that this brute force linear process, that we capture everything we need to build this useful index at the end, right? So the basic unit is we need to get all of the occurrences of a term and its paired document ID, right? So we will first record each term document occurrence. Then we sort them all to make sure that they stay efficient, right? We're going to first sort by terms, and then we will sort by the document order. We'll talk about that. And then we will merge all of those occurrences into postings. And that is ultimately the index. So let's do this. First, we will record each term document occurrence, top to bottom. Let's do these two little chunks of Shakespeare. So, document 1, I did an act of Julius Caesar, I was killed at the Capitol, Brutus killed me. Yes, of course. So, let's do it. The first occurrence is I in document 1, right? The second occurrence is did in document 1, an act in document 1, Julius in document 1, and so on. So, if we do this, top to bottom, record them all, okay, this is a bunch of occurrences. We have taken this document, these two documents, and turned them into just this sort of loose structure of the content, the term, and where it lives. The term and where it lives, right? Okay, so now where do we go from here? Well, we want to sort these things, because remember, your index in your textbook is certainly sorted in alphabetical order to make things much more simple. We sort them by term, but we also want to make sure that the document IDs stay in the proper order. So that this will make things easier for us later on. So let's look at this. If I'm going to now sort all this information, what will this look like? If I sort this, well, looks like, do we have any A's? Ambitious, that seems to be one. We have B, okay, we have blah, blah, blah. Let's do it. Ambitious, B, Brutus. Brutus occurs twice, interesting. That will be a list of postings that spans both of these documents. Just pointing to the future. So, we've sorted the list of occurrences. Cool. Now we need to actually convert them into some kind of searchable index, right? To do that, the final step is to merge these occurrences. First, we'll merge within a document. So if an occurrence of a single term happens multiple times, right now we don't care about that so much. We're not especially deeply interested in whether an occurrence happens multiple times in a document. In the future, we might be. In fact, wink, wink, we will be. But for now, this is just a broad binary thing. If I only care if the word Brutus occurs in the document, I don't care if it happens 75 times in that document. I just need it to be there at all. So first we sort, we merge within the document, we kind of lop off all the occurrences that are multiples. But then we do it between documents, so that a term that occurs in document 1 but also occurs in document 2, we are now merging those two occurrences into a list of postings, a list of multiple documents where this term lives. Let's do that. So if I'm going to build an index here, we're going to run through and we're going to say, okay, ambitious, that's fine. The one-offs are all okay. It's the ones that happen multiple times that we have to make sense of. So, for example, an example of merging within a document will be I. Look at I happens in document 1 twice. There's also the I apostrophe. We'll leave that as its own thing. I think it's short for in. That's Shakespeare for you. And that's also an example of a time we might actually want the punctuation, because it's not the same concept as I, right? But back on track. I occurs in document 1. I occurs in document 1 again. We're going to collapse that first, so that who cares? I don't care how many times it occurred. It just happened, right? Okay, so that's an example of merging within a document. An example of merging between documents would be, say, Brutus. So Brutus happens in document 1. Brutus happens in document 2. This is where we will create a list of postings for Brutus that says, oh, Brutus happens, where does it happen? Documents 1 and 2. Caesar is an example of both of these. So we're going to have to collapse the number of times Caesar happens in document 2, but then we will also create a list of postings based on Caesar happening in both documents. So let's just chunk through it. All right. This is an index. This is a list of terms. This is also kept track of document frequency, how many documents it appears in. That's not terribly important. This is from the text, that text I mentioned. Still don't necessarily need to read it, y'all. But it's available to you. Anyway, the terms are sorted. We have now a list of all of the terms that happen in these two tiny documents. And we have where they've happened. We have ambitious happens in document 2. We have Brutus happens in document 2. So if I want to say, ooh, where we talk about Brutus and his ambitions, I might create a query that says ambitious and Brutus. And while processing that query, I'll say, where do these terms live? Well, they don't both live in document 1, so screw that. They do both live in document 2. That's the one I'm going to pull out for the user. So that brings us to how to build an inverted index in this concept. These are all key, right? But the very first thing is just run through and write it all down. Term, document, term, document, term, document. Then the sorting helps with all the rest of the processing that we do, both right now and in the future. So we'll actually talk about that more when we talk about how to process these different queries. But finally, we merge all these occurrences, because we're going to have a lot of occurrences. We need to kind of winnow that down into something smaller and more useful. So that's how this works. So when we are implementing these things, how do we do it? What are some ideas for how to implement these steps when I go to actually do this in code, right? Well, first, the recording, like I said before, is just a linear scan of the tokens. It just creates little objects, or simple as small lists that are, what is the term and what is the location of its document? What is the term? What is the location of its document? Right. Then we do sorting. Now, sorting is typically a difficult process. It's hard to do when you have large sets, but thankfully, sorting is something that has been solved by most programming languages for us. So remember, we are going to talk about the theory of how to build every last one of these things, but when it comes time to actually do it, we'll rely on tools that exist, because we're human, and building one of these tools, we should use the most efficient tool available. Now merging, you got to scan a lot. You got to do a lot of like looking for repeated terms. There's more steps involved when you do a merge, but it's still mostly a linear scan. So we scan through linearly a few times of all the text of the document, and what we get on the output end is an index, which again, great. It's the shortest path to finding documents. So, after your documents are tokenized, we're going to keep digging in, right? So how would we build this recording function if we were going to do this? We're going to take tokenized document. We're going to record all of the occurrences in it, and then we'll do other stuff with that later. So how do we do that? Well, we have to get the documents tokenized into terms. Okay, that's the precondition. We're going to record all the occurrences. Now, what is that? You need some kind of small structure, so a very short list or a 2-length array to hold the term and the ID. Now, a document ID is, in our purposes, it'll probably be the index, the location within an array, known as the index in programming, right? But a different thing from the inverted index. So the document ID will be just the shortest way for us to recognize where something lives, right? So if I have an array of 1 million documents that I'm calling my collection, the address in that array where the document lives is its ID. So we walk through the text and we keep track of each term, each tokenized term, and the ID of where that term lives. Text, number, term ID. Right? How do we sort? Okay, now, as I mentioned, sorting is kind of a pain. Once we have all the occurrences, right? These are the currency of this. We are going to reorder them in terms of term and then also in terms of ID. Right? So this is time consuming. There's to touch on big O concepts again. If you do this manually, you're going to be looking for the lowest value, scan for the next lowest value, on and on and on. You're going to have to do a lot of moving things around. You ever try to sort something in person, right? You know, you don't want to spend all day on these things. A lot of comparisons. There are better search and sorting methods that get not n squared, but n times the log of n, something like that. Okay, so that's good. We are not going to focus on how to implement sorting. I promise you that. There are sorting functions that we can use that will tackle this stuff for us. But here is what the result of that sorting process looks like. So we've sorted by term first, right? And then by IDs. So and is the best example here because all the rest of them only happen once. And in these two documents, one dogs and cats, and then apples and bananas and oranges. So and happens in document 1 once, and it happens in document 2 twice. Remember, we will merge these later, but this is how we get them into the process, into the arrangement that we want. Okay, so why are we sorting? Why are we, if this is such a slow process and it's a real pain, why do we do this? So it helps you shortcut a lot of the search, right? When you look in your index in a textbook, you know not to search. You don't have to linearly search through all the A's, right? To get to your term cat, right? You jump straight to the C's. Algorithms can do that too in many ways. So the idea is that by keeping, remember, introduce as much structure as we can to this process so that on the output end, when we're Google trying to return something in 0.081 seconds to the user, it's fast, right? We don't want to have to redo any of these processes, so we do it all up front. So anyway, for an example of this, if I'm looking for apple, and I'm doing this linear search through the text, through the terms in my index, but I run into the word banana in the index, well, shoot, that means that apple is not likely present. I'm not going to find the word apple in the index. I don't have to run all the way through to Z to figure that out. That's a way that you can use the fact that your list is sorted as a shortcut. You can say, oh, well, hey, B is bigger than A. We're out of here. This term is not in this collection. These are important because the more times you have to run through the full list of anything, the longer everything's going to take, longer all your processing will take. So, okay. There's also, I said before that term frequency isn't super important, and then I badmouth the text. I still badmouth the text, but the term frequency is quite useful in some cases. You could sort your whole list not alphabetically, which is the way we're used to thinking of like efficient search, but say we might structure the dictionary of the index such that the high frequency terms are at the top. So I don't have to run all the way to the end to find right? That's going to show up quite a lot. Or more accurately, say I'm building an index of I don't know, types of cats. I'm going to stick to cats. Cats are easy. So I'm building an index of types of cats. The word cat is going to be quite frequent. I shouldn't probably wait to run all the way to the C's in the index if I'm going to be searching that way, right? So the idea here is the way that you sort helps you shortcut in different ways. And to that point, a lot of the methods we'll talk about as we go forward in the course are only possible to achieve with these sorted lists. So, as I mentioned before, when we actually go to sort in a programming world, sorting is a fairly solved problem. Any programming language has functions built in to sort. Java by default uses both quick sort and merge sort. Python uses this concept of tim sort. These won't mean anything to you. I'm just labeling them because this is accurate. These are all like well-developed methods of sorting long lists of information using different criteria. The differences don't super matter for us. We're sort of at the floating near the top. We're talking a lot about low-level implementation in the theory of the course, but when we go to do this stuff, we're going to use most of what's available to us to make it as simple as possible, and you'll see. So there's no big difference between all these. Just remember, sorting is costly and important. So we'll discuss the alternatives if and when they become relevant. But for now, the idea is sorting is this very key step. We need to do it, so we do it when we build the index. And from there, we don't have to worry about it again, which is great. Now, to that end, when we go to merge all of our terms, we will really benefit from the fact that they are sorted. So, merging is easy with a sorted set of terms. You're not terms, the occurrences, right? The terms and the documents, the document IDs. So this is actually pretty simple. When they're sorted, it makes it very easy. So scan through, and you can just find the duplicate occurrences, right? So we can merge within the documents by eliminating occurrences that happen that are identical to the one I'm on, right? So if the next one is the same as me, delete it. And then if the next one has the same term but not the same document ID, collapse it. Just put it on the end of my current list. So and ends up with both 1 and 2 as its IDs. Cool. So let's do another example because there's a lot going on here. But let's do them, right? So how are we going to build an index out of green eggs and ham? This one passage that we've seen before. Well, the first step is to record occurrences, right? Would you like green eggs and ham? Those are all in document 1. I do not like them. Sam I am. Sam I am is one token in this case. I do not like them. Green eggs and ham. Would you like them? Of course, right? We've run through the full text and logged all of the occurrences of the terms with their appropriate document IDs. Now we will sort them. Okay, so we're going to have there's a lot of overlap, right? Green eggs and ham show up a lot. We're going to sort them, alphabetical order and postings order. So let's just do that process. And anywhere, do, eggs, green, ham. Oh no, ham, here, right? And all the way down until we get to you. Okay, so we have sorted all the terms using the sort process that we won't dig into, but the idea is they are now sorted both alphabetically by term, and then within that, they're sorted properly lowest to highest in the document ID order. Okay, so now we merge them. What will happen? So looks like and will get collapsed to and will show up in documents 1 and 3. Good. Same process for a lot of these. And I think ultimately we don't have any within document occurrences to merge. So these will just be across document building the postings. So let's get our terms in order first. Okay, and anywhere, do, eggs, green, ham, etc. Good. All right, they are sorted alphabetically. And then we compile the postings. So great. And occurs in documents 1 and 3. Do occurs in documents 2 and 3. We're starting to see how we can maybe run similar processes like we did with the term document incidence matrices. We can now compare the postings of 2 terms and say, hey, where does that live? And I hope that illustrates why this is powerful. We've done a lot of work up front. We've done a lot of linear scanning. We've done a lot of expensive sorting. We've done a lot of compiling. But now we have this structure that will be quite useful. Okay, so we've looked at this in great detail of how one of these structures is constructed, how we make sure it stays fairly efficient. Now, one important part of this course is understanding how these things scale up as well. So we have the sort of the toy examples that help us understand how they work on a conceptual level, but we also need to think about the implementation in something like Google. So, scaling up. Again, we looked at the structure of these indexes in in deep detail, but how would Google handle this? How would we handle this if we were working at Library of Congress, right? Of course. 10 documents make sense to us, at least according to the way we've done these examples, right? But what about 10 billion documents? Now, any given term is only going to show up in some small percentage of these documents, but when you have 10 billion documents, that's still thousands or millions of postings for each term. Now we're kind of ballooning up to the same size issues that we were talking about with the term document incidence matrices, right? So how the heck do we stay efficient in this way? Well, one important concept that we haven't touched on much yet is the idea of storage. How are we storing things? So we're talking a lot about optimization, right? And just in theory, what are the best ways to make sure we don't have to waste cycles when we're doing this very big task, right? Runtime is big. We've talked about big O notation, how different algorithms will scale up poorly or not. But storage is also key. So we don't want to use slow storage very much. Storage isn't a big deal for our current work that we'll be doing, but we have to consider how storage fits into the bigger picture so that you can be familiar with this. So, some basics on storage. There's a big difference between memory and disk. these are kind of loose terms, but your RAM in your computer is a small set of memory you have made available for the computer to very quickly do lightning fast operations on. Whereas your disk is like your hard drive or solid state disk. Now that is also much faster than the hard disks of old, but it's still in general slower than memory. So memory is limited capacity, but it's extremely fast. So it makes it ideal for doing all kinds of operations that we need to do the data processing on a lot, like sorting, comparisons, recording occurrences for each document, that kind of stuff. Whereas the disk has an extremely high capacity, almost infinite. If you consider, you could just keep adding hard disks to your storage system, but it's very slow. So this is good for storing larger pieces of information that you only access once or a few times. So we might store documents there, or we might actually store our incredibly large list of postings there, because we only need to access postings once we've got a query to work on. You don't need to do it all. You don't need to hold that in the lightning fast memory. So that's one of the beautiful things about inverted indexes, is that your storage you can split the structure of an index up over its terms and its storage. So again, 10 documents versus 10 billion. You can hold the dictionary in memory. This will make it very quick for you to process. Oh, a query's coming in for cats and dogs. Okay, so you look up in your dictionary now. Every term has some set of postings associated with it, right? But you don't need to keep them in memory. You can now say, they need the postings for cat and the postings for dog. Okay, we're going to go to the storage. We're going to go to the disk, grab those postings. We'll do our processing of the query, and we'll go back and now look on the disk. Where is this document actually stored? Right? So, putting all this together, we have this process. We collect, tokenize, and otherwise entirely pre-process our set of documents, our collection of documents. So we have a tokenized collection. We run through the indexing process that we've gone over here, and we're going to record the term occurrences. We're going to sort them, the list of those occurrences. We're going to merge them into an inverted index. Great. So what's in the index? We have the dictionary of all the terms. It's a list of every term. It's nice and sorted. It's kept in memory typically, and it's great for fast search. We have built this dictionary that is quite searchable. Then we have the postings, where all the documents live, lists of all the document IDs associated with each term. And then we can keep this on disk if we have a particularly large collection. And we don't need to keep it in the search. We just need to access them when available. We're not kept in memory. So, building an inverted index. Woo! This is an intensive process, but we only have to do it once. Or sometimes occasionally if we need to re-index certain things that might change, or our collection kind of shifts under us, like in the Google sense. But we index a collection one time. We do this very intensive process once to create this big, messy, terrible search problem into one that is pretty linear. It's very much efficient. I run through the list in the index of my textbook until I find the term I'm looking for, and then I know exactly where that term will show up. Versus having to scan through the textbook with my eyes, hoping I draw some connections that help me figure out where that concept lives. The advantages of the inverted index, again, it's very easy on search. The query comes in, you search the postings, compare, and then you return the documents. We'll talk about that process later. Just this is the idea, right? We now that we have an index, the queries are very easy to make into something that interfaces easily with the index. It's very easy on storage, so we're not keeping track of what doesn't occur, like in an incidence matrix. We only keep track of what does occur, and we can split these different substructures up as needed across different methods of accessing the information. You could store the dictionary in memory, the postings on disk, and maybe have all of the documents on the internet. That's the Google way, at least. And we can keep extending this. But that's the other beautiful thing here. Now that we have the basic idea of the inverted index down, we can start adding new interesting functions to it. We can keep track of the term frequencies within a document, like we talked about before. That could be useful. We don't need to do that at the start, but it's easy to add it now, because we can, if we're storing all this information in a set of postings, those postings can get a little bit more complex. We can add more information to them to really increase our capabilities in terms of how we search these documents. So there's also, we'll talk about a few different structures for how to structure the dictionary, lists and search trees, and spoiler, the secret key is hash tables. We'll talk about those later. And different ways to sort, all this good stuff. So this is great. This makes a structure that is much more usable. We can search a huge set of information in a much more straightforward way when we have an index available. Now, the last tidbit though, when it does come time to process a query of, hey, I need documents that contain this word and this word, there is one fairly large disadvantage of doing this with postings as opposed to those nice incidence matrix rows. Postings are a list of document IDs, whereas the bit strings are these nice Boolean strings where are Boolean operations that we need. So, hey, I need term A and term B in my documents. That was simple and linear for them. Boop, 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 right? We end the documents and we find out where they live. But comparing lists, back to runtime issues. Comparing lists is non-linear. So if I'm going to say, hey, so for terms A and B, document 1, is that in both lists? I have to compare all of the postings of A and all of the postings of B to figure out that it's in both 3 and 6, unlike the linear process from the term document incidence matrix. How do we shortcut this? Is it possible to make this a linear process so that if we have 10 billion postings, we don't have to run through it 100 trillion times, right? So that is the topic of next time, and we will talk about algorithms to make that that comparison process shorter. Okay. Thank you for bearing with this deep dive. This stuff becomes the basis for the rest of the course, but we will reiterate quite a lot. So don't, keep track of this stuff. Try to work out how it works, and when we're going to start to have assignments soon. So now, final thought. As always, I want to leave you with something to just cogitate on a little bit, make you think about how this stuff fits in more broadly. So, where might you make good use of this kind of indexing process in your life? Take care.